Good evening. This is Andres Marty from Key Curriculum and McGraw-Hill Education. Um, Today's webinar features Daniel Scher, Senior Scientist at KCP Technologies, and the topic is Numbers in Focus with Sketchpad. So without further ado, the presenter, Daniel, I'm your MC today. My name is Andres. Please use the chat panel throughout the presentation to ask questions or to make comments. I'll be moderating the chat panel. Um, And I will now change the presenter to Daniel.
Thank you, Andres. Just to check, can you hear me okay?
I can hear you fine.
Great. So welcome everyone to Numbers in Focus with Sketchpad. I'm excited to be doing this webinar tonight because we're going to be showcasing a number of very new Sketchpad models. In fact, two of the models I'll show tonight are brand new, and I made them just in the last few weeks, especially for this webinar. And the number activities that you'll see tonight come from a grant that I've been working on for the last several years called Dynamic Number. Now, everybody thinks of Sketchpad as very dynamic when it comes to geometry. If you look on the screen right now, you can see this point that is tracing out the logo of KCP Technologies, and it's moving and in action. So the purpose of our grant was to move beyond geometry and think whether we could make numbers as dynamic as geometry is made with Sketchpad. So you're going to be seeing a number of examples of that tonight. And these are all activities that have been tested in classrooms. In fact, I want to give a special shout out to Tony, who I see is online here, who has helped with that testing here in Brooklyn. So let's look at what the agenda will be for tonight. We're going to look at these activities. Our very first activity, Jump Along, will feature a rabbit that's hopping along a number line, and it can hop by two different amounts, and our goal will be to see where that rabbit can land on the number line. We'll be looking at a factor array, where you'll be arranging a collection of dots so they can form different sized rectangles. We'll look at another factor activity called factor patterns, which color codes an array of numbers based on whether the numbers are factors of a given number. We'll look at a fun activity called number codes, in which the digits from 0 to 9 have been replaced with letters, and our goal will be to figure out and crack the code. We'll look at an unusual activity called color calculator, in which the digits of a calculator are replaced with colors to create a very striking way of thinking about decimals. And if we have some time at the end, we'll look at one of my favorite puzzles that we've created called set puzzles. So just a word about these activities before we start. These are all activities that have been pre-made with Sketchpad. They can be used by somebody who's never used Sketchpad before. You don't need to know anything about construction to do them. And these are all activities that are available for free on our Dynamic Number website. And we'll see the link to that at the end of this talk. I should also note that all of these activities come with complete teacher notes, worksheets, and videos. So they are very teacher-friendly. So let's get started. And we'll start with Jump Along. So here we have this cute bunny on a number line, and the bunny is starting at 0. And we have a jump by that's equal to 1. Well, let's see what happens if we have the bunny jump by pressing this red button. And let's press it a few more times. So notice that the bunny takes jumps of 1 to go from 0 to 1 to 2 to 3 and 4 and so on. So one of the questions we might start asking students is, what are all the different places where this bunny can jump? And pretty soon the students looking at this say, oh, well, this bunny can jump to any value. And we say, really, any value? And then they become a little more precise in the way they talk about this and realize that, well, not just any value, but those values that are greater than 0, and in particular, integers. So we can get to any value, like 25 all the way over here, although it would take a while by jumping by 1. So now I'm going to move the rabbit back to 0. And our next question is, okay, well, what about these numbers over here to the left of 0? How can we get to those? Well, we can change this jump by to a -1 just by typing inside that edit box. So let me do that. So now our jump by is equal to -1, and if I press jump, the rabbit now jumps to the left to -1, and it can continue jumping to the left, and now we can reach all the negative values. Great. So let's move the rabbit now back to 0, and let's try a different jump by value. Let's try, how about 2? And this is a sketch, of course, we can be using with very young children. And there are a lot of interesting questions we can ask just by changing these values. So let's say the jump by value is 2. Well, what values can we reach now along the number line? Now, the way this webinar is conducted, I'm going to be giving you a lot of answers right away to these questions, and it would be great if we were all in the same space and we could be discussing these. This is not the way I would like to teach the class. So when I ask a question and I pretty soon give an answer, realize that this is just as a way for you to see a lot about what this activity can be made to do, but is not the pedagogy I would recommend. So with that in mind, if we jump by 2s, students can be looking at the values where the bunny reaches and see, oh, 2, 4, 6, 8. Well, what's special about those? Well, those are the even numbers. And this is a nice way of seeing how bunny hops can relate to the even numbers. Well, let's move the rabbit back to 0 and ask a different question. Is it possible for the bunny to be able to hop just to the odd numbers? Well, notice we have 2 different jump bys. We've been keeping the second one equal to 0, but let's try changing this one. In fact, let's make it equal to, say, 1. So now if we do a jump by 1 and we land at 1, well, now at this jump of 2, we can go from 1 to 3 to 5, and we can hit all the odd numbers, again jumping by 2, but starting at 1. Okay, again, let's move the rabbit back to 0. And let's think of what else we can ask students. It would be interesting, actually, if any of you in the chat panel, if you have any ideas for some ways you could use this, after I'm done showing you just a few more ideas, maybe then Andres could look at these and share some of your ideas, because I'd really like to hear them. So what else could we do with this? Well, with jumps of 1 and 2, one of the questions we could ask is, how can you reach a given number in the fewest number of jumps? For example, how can we reach, say, 17 over here? Well, we could, of course, jump by 1s, but our other strategy could be to jump by 2s, getting as close to our target as possible, which, again, is 17. And we stop just short of 17 at 16, and then we jump by 1. So a pretty simple line of reasoning, but for young kids, I think this would make for an interesting challenge to ask, how can you get to these numbers in the fewest number of jumps? How can you get to them in the most jumps? So let's move our rabbit back to 0. And this time, let's see, what should we try next? How about if we set these 2 back to 0, and we ask students, how can you get to 13 as quickly as possible? Well, that's pretty easy. We're just going to set the first jump by to 13, and we'll jump, and kids love the big jump here. So now we're at 13. And let's say we'd now like to figure out a way to get to the numbers that are both smaller than 13 that we missed, 1 through 12, as well as numbers that are larger than 13. So how could we do that? Well, one idea that came up in one class was to set this value of jump by equal to minus 12. And let's think about that and see what happens. So we're at 13 right now, and if we jump by minus 12, let's see, that takes us back to 1. And where are we going to go next? Well, we're not going to get anywhere here between 1 and 12, but we could jump by 13 again and get all the way to 14. And from 14, we could jump back by 12. And we can form this really interesting pattern because we see the arcs that the rabbit makes, and we can keep jumping back and forth. Another idea, of course, is to set this jump by value equal to minus 1 and jump from, say, 13 back to 1, and then jump by 13 again. So there are a number of different ways this could be solved. Okay, let's look at perhaps one more challenge. I'm going to change jump by to 3 and our blue jump by to 5. And let's look at which numbers along the number line we can reach. Well, we can't reach 1 because these are both positive numbers. We can't reach 2. We can reach 3. We can't reach 4. We can reach 5, obviously. We can reach 6 as 2 jumps of 3. I don't see a way to reach 7, but let's look now what happens when we get to 8. We can reach 8 as 5 plus 3. We can reach 9 as 3 jumps of 3. We can reach 10 as 2 jumps of 5. We can reach 11 as 2 jumps of 3 and 1 jump of 5. And we can reach 12 as 4 jumps of 3. So I'm going to use the marker tool, and what I'm going to do here is I'm going to draw a little circle around these numbers that I just mentioned. 8, 9, 10, 11, 12. These are numbers that we can all reach, these 5 numbers. And what's interesting about this is that knowing that we can reach just these 5 numbers, we can now reason about why it's possible to reach anything greater than 12. And why is that? Well, if our bunny gets to 8, let's get the bunny to 8. Well, now the bunny can hop by 5, and the bunny reaches 13. If we can get the bunny to 12, which we know we can, let's just do that. Oops, that erased. Sorry. If we can get the bunny to 12, actually to 9, I'm sorry. From 9, we can jump by 5, and we can get the bunny now to 14. So by starting at any of these 5 numbers and jumping by 5, the bunny can now reach, oops, wrong tool, the marker tool, these next 5 numbers. And we can keep using that same process to obtain the next 5 numbers in the bunny jumps. This is actually something a little way more sophisticated than just some first or second grade activity. This is related to a problem called the postage stamp problem, where you're given 2 denominations of postage stamps, and you look at what denominations you can make based on just having 2 different postage stamps you can use. So there are a wide variety of ways you can use this model. And let me stop here to see if anyone else has any questions or perhaps suggestions for what they might do.
So there haven't been any questions so far, Daniel. The only question that's come up so far is whether we have anything for the tablet. And I said that we have an iPad version, and I just want to verify that everything that you're showing us today can be used on the iPad, right?
Yes, I think, let me just take a quick look. Everything here tonight can be used on the tablet, on our iPad. If you download this model when we send you the link to it, you can open it on the iPad, and it should work great.
So at the you'll receive a an email after the webinar tonight that has a link to Daniel's sketch, and then from there you can download the sketch, and you can download, if you have an iPad, you can download Sketchpad Explorer from the Apple App Store. Also on a regular computer, you can download Sketchpad and in preview mode use it. So I see there's another question. Yes, Leslie, there are plans to develop full versions. Those things are being developed right now. But anyway, no other questions. And yeah, Adrian made the comment, Daniel, that this could be extended to teach adding and subtracting integers.
Absolutely.
In fact, I believe that one of our free activities that you can download from the Learning Center or from the Key Curriculum website addresses that. Well, actually, that might be one of the Sketchpad lesson link activities. But yes, Adrian, you are right. And I will pass it back now to you, Daniel.
Thanks. I should mention that this bunny activity is a new one, but it's based on a whole collection of activities with bunnies jumping on the number line that teach things about factors and addition and subtraction. So let's look at a new model now. And this model is called factor array. And what we have here is a collection of 12 dots, 12 red dots, and they're framed by this rectangle. And what I can do is drag this blue point that sits at one corner of the rectangle. And when I do, it changes the number of dots that sit in my rectangle. So I can go from 12, where everything fits, to 11 dots with one left over, to 10 with two left over, and so on. As I drag this point, the positions of the dots change, but the number of dots stays the same. There are always 12. So I can actually move this frame around, and students can look at ways that they can create rectangular frames that enclose the entire set of 12 dots. So for instance, here we have a 2 by 6 array. Here we have a 3 by 4. We've already seen what happens when we have one row. Well, here's one column. And what I really like about this is the fact that as I drag this, I'm dynamically changing these dots, but there are always 12. So when I refer to something as this idea of dynamic number, to me, this is really the essence of it, being able to take something like the number 12 and very quickly being able to put it together in different ways to look at the factors. Here we see that 3 and 4 are factors of 12, and we can also see the commutative property that if 3 and 4 work, then if I turn my array the other way, then 4 and 3 will work as well. So right now we've only been looking at 12. Kids, of course, will want to look at much bigger numbers than 12. So let's look at, we'll say 50. So immediately when I type 50, I have 50 dots, and students can be looking at ways to frame those dots. And, ooh, can I reach? Good. So here we have a 2 by 25. We could also do a 25 by 2. And we can get into some interesting questions. So here we have a fairly large number, 50, and we're able to accommodate 50 dots on the screen in this rectangle with nothing left over. Well, what about if I make that number just a bit larger and change it to 53? Can I now fit these into different rectangular frames? And I can try for a while, and I might think I've almost got it, but no, I don't. And I can work and work, and oh, I could get one row with 53 dots, but wow, that's going to extend off the screen, and well, ditto if I go this way. So we can begin looking at the idea of what is a prime number? What does it mean that 53 is prime? Well, that means you can fit it in like this so that we can't see all the way up, or you can fit it across like that, but you can't get any other arrangement of them. And what's great about this is you can just on the fly change these to different values. If I can change 53, I can make this say 100. and see that I can do things like here, 10 by 10. Another nice thing we can do with this model when things don't fit so perfectly, like say here, is to look at what this represents. So here we have, if we look at this, we have an 11 by 9 frame that's enclosing everything except this one dot. So we could say that 100 is equal to 11 times 9 plus 1. Or, let's look at a different one. Here we have a 13 by 8 frame, and it's not entirely filled by dots. And we can say that 100 is equal to 13 times 8 minus 1, 2, 3, 4. So I made this model and brought it into class, and students very quickly wanted to give numbers much bigger than 100. So I also provided a second version of this with smaller dots, which should allow us to view larger numbers. So here we have 500 circles. And while I wouldn't necessarily ask students to go sit and find all the different factors of 500 and think they would be happy to do it, if you give it to them in this model and ask them to experiment with this frame to try to get all those dots to fit inside that frame, there's just something very pleasing about getting that to work and getting these to be perfectly inside there. And it gets students to have the motivation to stay at it and to have a very visual model of thinking about factors. So let me pause again and see if anyone has any comments or questions.
Well, the main question you got from Kurt is, hey, can you outline how you did this in Sketchpad? He thought he didn't think it would be possible. I was just in the process of saying that it would quickly become a very advanced topic rather than a beginning webinar. And my guess is that you used iteration, but that's just for the audience in general. I just want to let you know that the webinar today is intended to show you models that are already built that you can use in your teaching with students, and it was not our intention to, in this 1 hour, show you how to build a model like this, which would be a huge. I mean, we have a whole course that does that. I was about to type into the chat panel, constructing dynamic demonstrations with Sketchpad. But we do have another question from Leslie. So with bigger numbers, is it frustrating for students who are not able to drag the big rectangle big enough, like 2 by 250 or something?
Well, I think that brings up the question of for values like that, it raises the question, do we know those work without having to see them? Because we're not going to be able to get 2 by 250. So there are um, ways of breaking 500 down into like what you just said, where we're not going to be able to see it, but we know that 2 by 250 would work. So having that ability to reason about something and know that technically it should work, but that our computer screen isn't large enough, to me is sort of a nice way of bringing up this idea of that not everything has to be so concrete that when we get to a certain level, we should be able to reason about it just through reason and not by having to see every single way of breaking this down.
All right, great. Thanks.
Okay, let's look at one more example of factors. And I should say off the bat that if you believe that students should be spending all their time learning to recite the factors of a number, this is not going to be the activity for you. But that said, if we feel that analyzing patterns and making conjectures is important, I think this next activity does that pretty nicely. So it's building off of what we just looked at with factor arrays. We again have, in this case, 15 circles in a 3 by 5 array, but this one gives a little more information about what we have here. Notice that we have the numbers from 1 to 15, and certain numbers are blue, in particular 1, 3, 5, and 15. And these are the factors of 15. And if I drag this red point and I make different arrays and we look at them, we can pretty quickly see that these blue numbers are always the factors of the largest number in the array. And this model, like the previous one, was built using some pretty advanced Sketchpad techniques. So when I made this model, I wasn't really sure what kind of questions to ask about it. I just thought it would be kind of cool to use the array model and show using either yellow or blue which numbers were factors of the largest number. So as I began to look at it and talk about it with some students, a number of questions and conjectures came up, and I want to look at just a few of them here. So wherever we drag this to make whatever size array, one question to look at is there any number that, regardless of how many circles we have, is always blue? And that number is 1, because 1 is a factor of any number that I can possibly make. And what about in the case where I make, say, a prime number? So I have 13 circles. How many different ways can I arrange these 13 circles? Well, that gets back to what we looked at on the previous page. I can either have one row of 13 or one column. So a question that relates to that is, which arrays have just 2 numbers shaded blue? And if I drag my arrays like this, well, I'm not seeing any that have just 2, but if I go back to my primes like 17, well, that's when I encounter arrays with just 2 numbers shaded blue, 1 and the largest number. And we can use this representation here as a way of getting into talking about the properties of primes, that primes have just 2 factors, 1 in themselves. If I make an array with one row of 20 circles, we could ask students to predict what other arrays can we make with 20 circles. Just like what we could have asked on the previous page if I made one row of 20 circles. But here we have some more information. We see that since 2 is a factor of 20, that's an indication that if I make an array with 2 columns, I should be able to get 20 circles. And there I have it. If I go back to 20, this also tells me, for instance, that I should be able to, since 5 is a factor of 20, make an array with 5 as the number of columns, and there I have it. Other interesting observations we could make: if our array has, let's say, at least 2 rows and 2 columns, then we know that this number in the top right corner, the total number of circles, is not prime, because if the number was prime, then it wouldn't have these 2 factors we see here with 3 and 3. Now this is sort of an interesting array right here. Notice it has 3 numbers shaded blue, 1, 3, and 9. And the question could arise, are there other arrays that have just 3 numbers shaded blue? And through some experimentation, students might at first say, well, 9 is a square number, so perhaps it's cases where we're looking at squares. But if I try that now with a 4 by 4, well, that has more than 3 numbers shaded blue. And let's see, 5 by 5, oh, well, there again, we're back to exactly 3 numbers. And they might begin to make the conjecture that if I have a prime number of rows and columns and I have a square number, then a number like 49 has just 3 factors, 1 itself and its square root. So that's something that can come up from this. Another question that might arise is, when do you have exactly 4 blue numbers? And we could look at patterns for that. So there are lots of different patterns that are possible to see in this array. And, excuse me. And I think this representation brings those out in ways that if you were just factoring numbers on paper, wouldn't be as dramatic. Let me pause again.
So no questions, just a lot of comments. People like this, and the last two sketches you've shown us are great for number theory and perfect squares and looking at factors. So there's some excitement out there, especially from Leslie and Mark. But I don't see any questions. So if anybody has any questions, Frank says that his lack of questions is due to being absorbed in what you're presenting. So I think you should keep on presenting.
Okay.
If you do have any questions, just go ahead and tap them in the chat panel, okay?
So now I'm going to dial back the years and show you actually a page from my fourth grade math book. And don't ask how I actually have this, but I do. And I'm not going to tell you which publisher it is. But in our math book, in the back of um, the book was fairly heavily focused on strict computations. There wasn't a lot that was interesting in it. And this was the 1970s, so not a huge surprise. But there was something that I found kind of cool. They would have these problems, like in this set of multiplication problems, and then underneath it, they would have these coded answers where they had taken the answers to the problems, and rather than just tell you what they were, they had employed a simple code where they had assigned, say, 0 to the letter D, 1 to the letter F, 2 to the letter A, and so on. And when I saw this, I thought, wow, this would be a lot more cool to crack this code and be able to figure out the values of A through J and then just write in the answers to all these other questions without actually having to solve these pretty horrific problems where I was just getting bored solving them. So I went ahead and I cracked these codes, and in my answers, I wrote down the code, A equals 1, B equals 3, whatever, and handed that into my teacher. And she was completely aghast at this and felt like I should have been spending my time practicing multiplication and not doing something as frivolous as cracking these codes. That always stuck with me because I thought codes were a lot more fun than just basic number practice. So I came up with two models in the last few weeks that I want to share with you that are inspired by this idea of codes. So here's the first one, and it's called mystery sums. And each letter from A through J has been assigned a number or a digit. So A might equal 3, B might equal 7, and so on. All 10 digits from 0 to 9 are represented here, but we don't know which letter represents which digit. We do have a few things we can do to help us figure that out. We have these two chips, and if I drag them, I can place them into any two boxes I want. And here we're looking at the sum of A plus C, and that sum is equal to J, where J is the ones digit of our sum, and there is no tens digit. If I drag this to say here, where I'm looking at A plus I, the sum written as a two-digit number is AE, where A is the tens digit and E is the ones digit. And our goal is to figure out what are the values of these 10 letters. So there are a number of observations we can make. And again, this is a case where I'm going to go way too quickly through this and would much rather give you the opportunity to solve it yourself. So warning, there are going to be spoilers ahead in this. So one thing we can do is to look at this and realize that, well, what does it mean to have a tens digit of A? Well, if we're looking at addition, then the only possible tens digit we could have is 1, because we can't get any higher than the sum of 9 plus 9, or 18. So I'm going to assume that my A is equal to 1, and I'm going to drag 1 over here so I can keep that in my head. Now, another thing students might realize when they start to play with this, and I know the answers, so I'm going to move ahead a little bit and show some stuff, is that if they put one of the chips on E and they drag the other chip around, it's kind of an interesting thing happens. C plus E is equal to C, C plus D plus E is equal to D, and wherever I drag this other chip, well, the sum is equal to wherever that chip is sitting. So F, G, H, I, J. What could that mean? What could E be? Well, normally if you talk about the fact that any number plus zero is equal to that same number, it's kind of a boring fact. Well, yeah, duh, anything plus zero equals itself. Here, when you have that moment of recognition that E is playing that role of zero, and that anything added to zero is itself, I think it's a lot more exciting. You've solved for the value of zero, and you've made an interesting discovery. So where could we go from here? There are a number of different routes we could take. One possibility is this. We've been dragging these chips so that they sit in different squares, but there's no reason we have to do that. We could, for example, drag the chips so they sit in the same square. So here, for instance, we have G plus G is equal to, oh, something we know, 1 and 0. So G plus G is equal to 10. So what does G have to be? Well, G is 5. What could we do from here? Well, what could we do? Well, one simple thing is to use that same strategy again. We can drag both chips into A and see that 1 plus 1 is equal to 2. So F is equal to 2. We could perhaps drag both of these into F and say 2 plus 2 is equal to 4, and that gives us 4. And we could continue on this route. And there are other ways we could go about solving it. When I have everything solved, I can press show answer and see the actual answers here. And if I press new puzzle, then if I drag these out, I don't have a button here yet that actually moves them back. Now we have an entirely new code. And for us as adults, maybe if we solve this once, we've figured it out and we get the strategy. For students, I think being able to play this repeatedly and being able to try different strategies and hone their existing strategies is pretty important. So naturally, after I did mystery sums, the thought came up, well, what about mystery products? Can we do the case where we're looking at the product of two numbers like B and D instead of the sum? So how can we crack the code in this case? Well, now we can't be so sure anymore that this number in the tens place, G, is equal to 1. It may very well not be equal to 1. So what might we do? Well, again, knowing a little bit about this here, let me try, let's see what we have here. Oh, that actually isn't the one. Let's see. Let me just play around with this a little. Now you're seeing what it's like to actually play with this. So again, here we found it. If I put one circle in G and the other circle in H, now when I move this circle around, this disk, from letter to letter, we see that the product of any letter times G is equal to that letter. So where before we looked at the identity element for addition and found that it was 0, here we're looking at the identity element for multiplication, so G must be equal to 1. If I put one chip in C and move my other chip around, this is also pretty interesting behavior. Now we see that wherever this chip goes, the product is always C, and well, that tells us that C is equal to 0. So rather than continue to solve this, I'm going to leave this one here and let you have some fun figuring out the other values and some strategies, and just quickly ask whether any of you have any questions.
John was asking if these challenges are being randomly generated.
Yes, these are totally randomly generated.
Marcy was at. Oh, I'm getting comments fast so that I can read them. Susan was asking, what's the primary age group you would suggest these with?
I've done activities like this starting in, say, fourth grade. One of the discussions we needed to have was about this role of what it means to be representing the product or the sum using two different letters, where one was for the ones place and the other for the tens. That took a little work to get that piece of it going. But once they got that, the addition, this first code was certainly something that everybody could do. The product, I would say, was harder. That one, we would have needed, I think, a little more time to give students to solve that. I was only in the class for one day when we did an activity like this, and that wasn't enough.
Marcy also commented on how these activities lead into a discussion of the properties of numbers and things like the identity property, properties of zero, and so on.
Very much so.
So that's it for now. Carry on.
Okay. Now we are going to look at um, representing fractions as decimals. And what I'd like to do is talk a little bit about just a standard calculator to begin. When I first got a calculator, I loved to just type numbers into it and see what came out. So for instance, I might type 1/7 and see this string of digits and be pretty interested in where that came from. But in this case here, I'm only seeing 6 digits. And today's calculators, if we had a handheld, could show some more, but they're not going to show that many more digits. Maybe you're going to be limited to, I don't know, on the iPhone how many there are. There might be 12 digits or a few more, but not that many. And Sketchpad's calculator here is no exception. So the question comes up, what would it be like if we could look at a fraction like 1/7 and see its decimal representation, but not just see it for this string of digits here, but what if we could keep going and see 20 significant places, or 30, or 40? What kind of questions could we ask about that? Now, this isn't going to be an activity that focuses on the traditional understanding of fractions, where we look at fractions as parts of whole, or we do the actual nitty-gritty of how you convert a fraction to a decimal. This is much more about looking for patterns, and is an activity that I don't even think requires students to actually know long division at this point. This idea for this activity, which you'll see develop in the next few sketches here, comes from Natalie Sinclair, who's a professor at Simon Fraser University in Canada, who has very interesting ideas about how to use Sketchpad with young kids. And this is an idea that comes from a book that she wrote that was published by Teachers College. So let's see what we can do. And this model gets back to our favorite array model, which we keep seeing, that we can represent numbers using arrays. So I'm going to take this red point and keep dragging. And each time I drag, we see more digits. And we begin to notice something interesting, that this pattern 142857 seems to be repeating itself over and over again. Oops. And I don't have to drag just straight across. I can start dragging down so that we're reading across this first row, coming back here to the second row, reading across, and reading across each time from left to right. And I can make this grow and grow and grow. Now, if I want to look for patterns in this, I can, but it's not incredibly appealing. I have to start looking at all these numbers, and it almost begins to look like a number word search to me. So Natalie had this very clever idea that since we're more concerned about the patterns than the actual digits themselves of the decimal representation, why not just use a color version of this, where we assign each digit from 0 to 9 its own unique color. So now let's move to color. And here we have that same representation of 1/7, but each digit has been assigned a color. And I can drag out, and I can drag down, and we're seeing that same representation just with color coding. So it's interesting when students start to look at this, what patterns they might find. Here, for example, we see this very nice diagonal pattern with the colors going down the diagonals. And if I keep dragging, we can see when we get to here, the fact that this is a repeating decimal, that the same string of digits, these 6 digits, whatever they might be, these different colors repeat over and over again. And the fact that we can choose how many of these circles are in each row allow us to see that repetition. So there are a number of interesting questions we can ask, and that, in fact, we just ask students to come up with some. For instance, what happens if we change this from 1/7 to 2/7? And we'd have to see both side by side here, but it's interesting that when we change from 1/7 to 2/7, we have the same string of colors. It's just in the same order. We're just beginning at a different color. And I can change this to, say, 4/7, and again, we get the same colors, just starting in a different place. So we can ask students some interesting questions. We can, for instance, ask them to find some fractions whose decimal representation has exactly one non-zero digit to the right of the decimal. For example, 0.6. And I'm saying it as 0.6 rather than the preferred way of 6/10 because I want students to come to that realization that, oh, if I have something like 6/10, then that gives me 0.6000000 and so on, an infinite amount of zeros. And here we have a fraction whose decimal representation terminates in all zeros. We might ask them to come up with a fraction whose decimal representation contains exactly 2 non-zero digits. So perhaps students would pick something like, oh, I don't know, 47/100. So again, we have all zeros, but we have 2 that are not zero. They could look at other patterns. For example, what happens if we look at fractions with a denominator of, say, 9? Well, here we get all the same color, and this, in fact, is 0.111111. And if we change that to 2/9, and we might even go back to the other model, we can see these are all 2s. In fact, we have a version here which combines the numbers with the color. So if I switch this to, say, 6/9, we get all 6s. And students might say, well, this works for everything. We might go from 6/9 to 7/9 to 8/9 to get all 8s. But what about 0.99999? And they try 9/9, and that doesn't work. In fact, they can't get 0.999 repeating infinitely. So there are some other interesting questions we can ask. We can have them look for fractions like 1/7 that repeat a sequence of digits over and over again. Can they find a fraction that has a really long set of digits and colors that take a while before they start repeating? So if we try something like, how about 1/17? This one, if we look to see how long it takes to repeat, this one takes a while. Here we see the diagonal patterns, and we have to go all the way out here to 16 places before we get repetition. If we try 1/19 instead, then in this case we have to go all the way out to 18 before we get repetition. And students might begin to make a conjecture like, oh, well, if 1/17 had 16 repeated digits and 1/19 had 18, then maybe it's the case that if I have a 1 divided by a prime number, the number of repeated digits will be 1 less than the prime, and they can check that out. Some other fun numbers to check are things like 1/81st. Here we have a very interesting pattern. We have 0, 1, 2, 3, 4, 5, 6, 7, no 8, 9, 0, and that repeats over and over again. So I really like this activity. It's completely non-traditional, um, but when you think about the fact that kids just aren't really exposed to this idea that we can have these fractions that some that terminate in zeros and others that eventually repeat, even if students don't know their long division or anything like that, the fact that you can be getting into these properties and making students interested in it at, I think, a pretty young age. I'm not sure exactly which grade level. I haven't used this one with students in the classroom, but I would say certainly by the time you get to 6th or 7th grade, I think it's pretty interesting. So let me pause again and catch my breath and see if anyone has any questions.
Um, Not really. There was a question earlier about in the last activity if the students would be working on different puzzles because they're randomly generated. I said probably so, right?
Sure, if you have
Yeah.
those puzzles at different computers, every time they press a new puzzle, everybody will be getting a different challenge.
And then there was a question if Sketchpad has any kind of what was it? It doesn't accept sound in any way, does it? I mean, I know there's a sound button now, but I don't think it doesn't take sound as an input. Correct?
No, it doesn't.
Okay. And now I just started getting some more questions. Um, yeah, the question of you joined late, will you be able to watch this from the beginning? Yes, we are recording this webinar, and in the email that yeah, if it was tonal was the question. So we will have that. When you receive the email at the end, it'll tell you how to access both the video that will be online. I'll show you that really quickly at the end, and you'll also be able to get the sketch that Daniel is showing us right now. Um, so the icons on the right remind me of Geometry Sketchpad. Is it related to this Sketchpad? Yes, this is. All of these are being. This is these models that Daniel is showing us, Susan, are all created in Sketchpad and require Sketchpad to run, but they are pre-built models built in Sketchpad that address uh, topics that span elementary grades and up. As you can see, a lot of these models were designed for elementary students, but then can become useful again at higher grades as you discuss number theory. Mark was wondering, how might you discuss irrationals?
That's a good question. Actually, in the calculator model that now Natalie Sinclair built, um, that I based this on, hers is not just a calculator that accepts fractions as inputs. There you can actually do things like square root of 2 and see its representation using this color coding to see that you're not going to get any repetitions. That's actually something I'd like to try to see if there would be a way to build a more robust calculator that would be able to introduce irrationals.
Okay, that's all the questions for now.
Okay, so I have just a few more minutes, so I wanted to show you one last activity quickly. Here we have two circles, and we have the numbers 1, 2, 4, 8, and 16. And our goal in this randomly generated challenge is to drag these circles and the numbers so that the sum of the numbers in the green circle is 9 and the sum of the numbers in the blue circle is 18. Okay, well, 9, I can drag the 8 and the 1, and my circle turns green because I got it right. And blue is 18, so 16 and 2. Ah, I got it. Piece of cake. Well, let's try a new challenge, randomly generated by Sketchpad, and see if the next one is as easy. And actually, that one is. Let's make a new challenge. Here we go. So now we want the sum of the numbers in the green circle to be 3. So that's going to be 1 and 2. And I want the sum of the numbers in the blue circle to be 30. So what do I need for 30? Well, 16, 8, 4, and what am I missing? That's 28, but I need another 2. So let me drag that out and move it over here, and oh, now my blue circle is right, but my green circle is not correct. So what do I do with this pesky 2 that needs to be in both places simultaneously? Well, I can move this circle so that it intersects the other, and 2 sits in both circles, and there. Now I have the right answer. And all of that can happen without having to tell students anything about the idea of sets or intersections. It's what comes up naturally when students are doing this. Now we move to 3 circles, and let me generate a slightly harder challenge. Notice now that we have the numbers here that are all multiples of 2, powers of 2, 1, 2, 4, 8, 16, 32. And these numbers that come up here are between 1 and 63. And it's pretty interesting that you can make any number between 1 and 63 just using these 6 numbers here. So for 44, I can drag 32, 8, and 4. I need 33. Oh, well, that's going to need my 32, so I'm going to move this here. Well, let me move these numbers over a bit. Often solving these challenges means taking what you had that works and rearranging things a little. So there, I'll drag this, so I have 33. And now I need, what do I need? 23. So if I have 16 and 4 and 1, how am I going to get that to work? So 16, I can move the 1 here, and 4 here, and 2. So this isn't even that easy for me to be solving these because we have 3 circles and an infinite number of problems that can be generated. There's a version here where Sketchpad gives you 10 problems in a row that are randomly generated, and you get points for solving each. Students like that. And since it's a puzzle, I really like the idea of students being able to create their own puzzles for each other. So if I was playing this with you, I could come in here and just type in any old values I like between 1 and 63, and then give you the challenge to solve, and then you could give me one. And depending how hard I made it for you, you might make it equally hard for me. So to conclude, all of these activities come from the Dynamic Number Project funded by the NSF. And if you go to our website by clicking this button in the sketch that you will receive, you will go to the Dynamic Number website, and the Curriculum tab has all of these activities. It has teacher notes, it has worksheets, it even has little movies that go with most of them that show you how the activity works. And I would be very interested if you use these activities to get some feedback on them because they're still under development. You can also find these activities in the Sketch Exchange, which Andres was talking about at the beginning of the webinar. And this last page of my sketch, which you'll receive, gives you information about where you can go to get our online tutorials, other free activities, activity modules. We have 2 elementary Sketchpad books, which contain lots more activities relating to number and geometry. The Sketch Exchange, where you'll find the dynamic number activities and other sketches contributed by our worldwide Sketchpad user base. There's information about training. You can take more webinars or online 6-week courses to learn in depth about Sketchpad. We have Sketchpad Explorer for the iPad, which is our free iPad app that allows you to take any Sketchpad model that you've built with desktop Sketchpad and open it on the iPad. And that's it. A wealth of resources at your fingertips.
Okay, great, Daniel. Your timing is impeccable. We're just about at 5 o'clock, and there was sort of a flurry of questions at the end about buying Sketchpad, and I sent the information out through the chat. Um, and now you're getting a lot of accolades from people who are appreciative of the many great ideas you've shared. A lot of great stuff there, and I want to thank you for an excellent presentation. I'd like to thank all of you for joining us today. I'm going to, well, Daniel's done a pretty good job of doing the ending. I'll go ahead and show my screen again for a second. So just show you a couple of things I mentioned in the panel. Again, you can just go to keycurriculum.com and go around there. You'll find information for the Sketchpad Explorer on the iPad there. If you go to our training webinars, the archived webinars, you'll find all of them there. It looks like Numbers in Focus is already being kicked into archived webinars automatically because it's after 5 o'clock now. And so this is the ones we've done recently, the March Madness with digital tools, sink your teeth into Pi with Sketchpad, and so on. Again, our online courses, the information is also at keycurriculum.com. We have a course that's specifically for teaching elementary math with Sketchpad, as well as many other courses for middle school, algebra, geometry, and advanced math, as well as our dynamic data softwares, so you can statistics with Fathom and middle school math with Tinkerplots. This is a new course we have that some of you might be interested in. The Constructing Dynamic Demonstrations goes more into how to build models, such as the ones Daniel's presenting. Yeah, the pricing information and so forth you can find here at Products, Sketchpad pricing. So, once again, thank you everyone for joining us this evening. We will leave the chat panel open for a couple of more minutes. I see a question about how you'll get the certificates. Those will be emailed to you directly, along with the links to the sketch that Daniel was showing and to where the video is archived. We appreciate you spending an hour with us on this Tuesday evening. And if you have any other questions or comments, just go ahead and use the chat panel. Once again, Daniel, thank you for an excellent presentation, and thank you all for joining us this evening.
Thanks, everyone, and thanks, Andres, for moderating.
Good night.
Night, everyone.